The following video is an outline of the basic theory behind antenna arrays, how they work, and why they are preferred over alternative solutions within given industries. An antenna array, often referred to as a phased array, is a combination of two or more antennas that are combined in order to obtain an increased performance over a single antenna by producing a higher antenna gain and providing capability of a steerable and directive signal. An antenna is a metallic structure that captures and/or transmits radio electromagnetic waves. It is an electromagnetic radiator. It creates an electromagnetic field that proceeds out from the transmitting antenna to the receiver's antenna, which then converts the electromagnetic wave into electrical signals that are applied to the receiver's input stages. Combining an n number of antennas yields an antenna array. The performance of the antenna array increases with the number of antennas used, with the drawback being increased cost, size, and complexity. An antenna array is a radiating system, with each antenna containing their own radiators. Each antenna element produces its own induction field, which is referred to as mutual coupling. The individual antennas are placed compactly in a way such that they lay in the area of another's induction field. The placement results in the vector sum of each of the individual's induction fields, producing a radiation pattern. Most antennas reversibly link radiation fields to current flow in wires at frequencies ranging from sub-audio through the far infrared region.
An antenna array is defined by two fundamental characteristics. One, it provides the capability of a steerable beam. Antenna arrays give us the flexibility to design a desired antenna pattern for transmitting and receiving signals without changing the physical dimensions by modifying the five following parameters. 1. The geometric configuration of the array. For example, the array can be configured in a linear, circular, spherical, or rectangular fashion. 2. Varying the distance between each element. 3. Changing the excitation amplitude of the individual elements. 4. Modifying the excitation phase of the individual elements. And finally, 5. The individual pattern of each element. We can also manipulate the received signals from the individual antenna elements in different ways to achieve many signal processing functions such as spatial filtering, interference suppression, gain enhancement, and more. In the latter part of this video, we will be able to see the effects of changing the excitation phase on the total field patterns. The second characteristic of an antenna array is that we see the gain of the antenna is increased. The gain of the antenna in a given direction is defined as the ratio of the intensity to the radiation intensity that would have been obtained if the power accepted by the antenna were radiated isotropically, which means that the magnitude of the antenna does not vary with the direction of measurement. In most cases, we deal with relative gain, which is the ratio of the power gain in a given direction to the power gain of a reference antenna, generally a lossless isotropic source in its reference direction. The gain is a measure that takes into consideration the efficiency of the antenna as well as the directional properties. If the direction is not specified, the power gain is usually taken in the direction of maximum radiation. As the gain of a directional antenna increases, the angle of radiation usually decreases. This provides a greater coverage distance, but with a reduced coverage angle. The gain of the antenna is increased due to the principle of pattern multiplication, which states that the total field of the array is equivalent to the product of the field created by a single element located at the origin and the array factor, which is given by the following equation. To better understand this concept of pattern multiplication, we will examine the far-field approximation of the two-element transmitting antenna array given by the following diagram. To simplify the math, we will make the four following assumptions. 1. Elements are identical in the phase and amplitude excitation and are equidistant from each other. 2. The radiators are non-isotropic point sources, which means that they do not occupy any volume. 3. There is no mutual coupling in the transmitting array. 4. The element radiation pattern is chosen to be non-directional so that the electric field is only in the YZ plane. Each element electric field is given by the following equation with the following parameters. And using the superposition principle, we can sum the total of the electric fields, which simplifies to the following equation. We can see that the total electric field is mathematically equivalent to the product of the field created by a single element located at the origin, denoted by EF, and the array factor, which is denoted by AF. It is important to understand that the array factor in general depends on the number of elements, in this case 2, the relative magnitude and phase excitation, which is given to us by theta and beta, and the spacing between the elements, which is given by the value d. To illustrate this concept, let us examine the normalized pattern of a single element, the array factor, and the total array for an antenna array consisting of two horizontal infinitesimal dipoles located at a distance d equals lambda over 4 from each other and with equivalent excitation magnitudes as shown in the figure below. The first diagram shows the element, array factor, and total field pattern when the beta value is set to 0. By changing the phase difference from 0 degrees to 90 degrees, we can see that only the array factor is affected, which allows us to manipulate the total array pattern. This example highlights the two fundamental characteristics of the antenna array. We see that the antenna array provides capability of a steerable and directive signal and also allows us to have a higher antenna gain.
Antenna arrays can be found in so many applications in our advanced society. Antenna arrays are used in mobile communication tower systems to help overcome the limited channel bandwidth. Therefore, companies can support more and more cell phones. Using antenna arrays in mobile communication systems helps improve the performance of the system by increasing channel capacity, extending range coverage, compensating aperture distortion electronically, reduces multipath fading, system complexity and cost, and outage probability. Hopefully in the near future we can have communication to a mobile device anywhere in the world. Another very popular example of the use of antenna arrays in our society is in the automotive industry. The advantages of the antenna array is significant in fading from the surrounding signals reflecting off nearby walls or other cars on the road. The antenna array with directional radiation pattern provide higher gain and immunity to the interference sources.
To summarize, antenna arrays are a combination of two or more antennas that have an increased performance over a single antenna by producing a higher antenna gain and providing the capability of a steerable and directive signal. These characteristics allow us to utilize antenna arrays in every technology, such as satellite communications, wireless communications, and much more.